Hello, viewers. In today's session, we are going to discuss an important and conceptual problem from limits. And here we are going to discuss the existence of this limit where the signum function is involved, right? So here we have to discuss the existence of the limit x tends to 0, and the function is the signum of x square minus x, right? So to discuss whether the limit of this function when x tends to 0, it exists or it doesn't exist, we have to make use of the concept of right hand limit and left hand limit, right? And here we'll also make use of the definition of signum function. So let us start. So let us first define the signum function. Now we know that signum of p is defined like this. That is, signum of p takes the value plus 1 when p is greater than 0, and signum of p is 0 when p is equal to 0, and signum of p is minus 1 when p is less than 0. So when the values of p are all positive, that is, the input is positive, then signum of p has the value plus 1. And when p is equal to 0, then signum of p is 0. It implies that signum of 0 is equal to 0, right? And when all the p's are less than 0, that is, all the values of p which are negative, then signum of p is equal to minus 1, right? So for this part of the definition, we can now write signum of any positive input gives us the value plus 1, and signum of any negative input gives us the value minus 1. So we'll make use of the definition of signum function to find out the right hand limit and the left hand limit. So now let us take this function as f of x. So we have f of x is equal to signum of x square minus x, right? And we have to now see, or we have to check the existence of the limit x tends to 0 of the function f of x. So let us first find the right hand limit. So the right hand limit, the notation for a right hand limit is given by limit, and here we write x tends to 0, and here we put a positive sign, and here we have f of x, right? So here we have x is equal to 0. So when we approach from the right of x is equal to 0, then here we have a point very close to x is equal to 0, and it lies towards the right of x is equal to 0, and this point may be taken as 0 plus h, where h is infinitesimally very small. So h is very small, but h is a positive quantity, that is, h is greater than 0. So now the right hand limit can be evaluated by taking this substitution, that is, x is equal to 0 plus h, and when x tends to 0, from the right of x is equal to 0, that is, all the values of x which are greater than x is equal to 0 are given by x is equal to 0 plus h. So when x approaches to 0, then h tends to 0. So now we can express the right hand limit in terms of h. So we replace x tends to 0 plus by h tends to 0, and here x can be replaced by 0 plus h. So we have now limit h tends to 0, and here we have 0 plus h is simply h. So now we have to write the value of f of h. Now f of h can be obtained by replacing x by h in this function. So here we have a signum of h square minus h. So now let us consider this expression, that is h square minus h. So we can now write limit h tends to 0, and we have signum of here we can take h common. So we have h, then we have h minus 1, right? So now let us consider the sign of this expression, which is the product of h and h minus 1. Now see, h times h minus 1. Now h is a positive quantity, that is h is greater than 0. So h is always going to be positive. And here we have h minus 1. Now see, h is infinitesimally very small, right? And h is greater than 0, but it is less than 1, right? So this quantity, that is h minus 1, is going to be a negative quantity because h is less than 1, right? So h minus 1 is going to be less than 0. So this quantity is negative. So now the product of h and h minus 1. So h is positive, h minus 1 is negative. So the product of positive and negative quantity is equal to negative quantity. So here we can now write limit h tends to 0, and we have signum of a negative quantity, right? So this product h times h minus 1 is always going to be a negative quantity, and we have just seen from the definition of signum function, that is signum of a negative input, that is signum of some negative number always gives us a minus 1. So here for signum of some negative quantity, it gives us minus 1, right? And now this term is a constant and it is independent of h. So this limit is equal to minus 1, right? So the right hand limit of this function f of x when x approaches to 0 is given by a minus 1. So here we write the right hand limit as minus 1. So now let us find out the value of left hand limit. So the notation for left hand limit is limit x tends to 0. Here we put a negative sign, and here we have f of x. So when we calculate the left hand limit, then we proceed from the left of x is equal to 0, and we arrived at a point which lies towards the left of x is equal to 0, but it is very close to x is equal to 0. So this point which is very close to x is equal to 0, but it lies towards the left of x is equal to 0, this point may be taken as 0 minus h, and here h is a positive quantity, right? So now we can take this substitution, x is equal to 0 minus h, because all the values of x which lies towards the left of x is equal to 0 are less than 0, right? So we have now x is equal to 0 minus h, that is minus h, right? And when x tends to 0 from the left of x is equal to 0, then h tends to 0. So now we can write the left hand limit in terms of h. So we have now limit, and for x tends to 0 negative, we have h tends to 0, and here we have f of x. X is 0 minus h. So we have limit h tends to 0, and here we have f of minus h. Now f of minus h can be obtained by replacing x by minus h. So now we can write limit h tends to 0. F of minus h is given by a signum of minus h square minus, and here we have minus h, right? So here we take x is equal to minus h. So now simplifying this expression, we have limit h tends to 0, and we have signum of minus h square is obviously positive h square, and here minus and minus, when multiplied together it gives us plus h, right? So now we have limit h tends to 0, and let us write this term as taking h as common. So we have h times h plus 1, right? So now let us consider this expression h times h plus 1. So here we have h and here we have h plus 1. Now h is infinitesimally very small, but it is a positive quantity. So here h is positive. Now h is positive and here we have plus 1. So when we add h to 1, then h plus 1 is again a positive quantity, because h is greater than 0. So 1 plus h is greater than 0, right? And the product of these two positive quantities is always going to be a positive quantity, right? So here h times h plus 1 gives us a positive number, right? So we have limit h tends to 0, and here we have signum of some positive quantity, right? And from the definition of signum function, we know that when the input is a positive quantity, then signum of some positive quantity gives us plus 1, right? So it implies that the image of signum of positive quantity, right? So all the positive quantities here has the same image, that is plus 1 under this function, that is a signum function, right? So we have limit h tends to 0 and signum of some positive quantity gives us plus 1. So now this term is independent of h, so we have simply here plus 1. So the left hand limit of this function f of x is equal to plus 1 when x approaches to 0. So now from this discussion, we have seen that the right hand limit is equal to minus 1 and the left hand limit is equal to plus 1. And we can see that although the left hand limit and the right hand limit both exist and they are finite, but they are not equal to each other. That is, the right hand limit is not equal to the left hand limit, that is minus 1 is not equal to a plus 1. So as such, the limit that is x tends to 0 signum of x square minus x, it does not exist when x approaches to 0, right? Because the limit of a function exists when we have the right hand limit and the left hand limit, both the limits are equal to each other, and provided the right hand limit and the left hand limit must exist and they must be finite, right? So in this case, the right hand limit and the left hand limit, although they exist and they are finite, but they are not equal to each other. Hence we can conclude that the limit of this function when x approaches to 0, this limit does not exist. Hello viewers, in today's session we are going to discuss another important problem from inverse trigonometric functions. And in this session we are going to discuss this problem where we are given this expression, that is square of sine inverse x over 2 minus square of cos inverse x over 2 is equal to lambda times pi square over 4. And here we have to find the range for lambda, right? So here we have to find out all the valid values of lambda for which this expression is defined where a lambda belongs to the set of real numbers, right? So let us see how we can find out the range for this parameter, that is lambda, using some properties from inverse trigonometric functions. So let us start. So now let us first apply the well-known identity, that is a square minus b square is equal to a minus b and a plus b, right? So here if we take a is equal to sine inverse x over 2 and b is equal to cos inverse x over 2, then this expression can be written as a square minus b square is equal to lambda pi square over 4. So here we can now write a minus b times a plus b, and here we have lambda pi square over 4. Now see here the value of a plus b. Now if we add a and b, then a plus b is sine inverse x over 2 plus cos inverse x over 2. And from inverse trigonometric functions, we know that sine inverse theta plus cos inverse theta is equal to pi over 2, when this theta, it belongs to the interval minus 1 to 1, right? So the value of theta in this case is x over 2, right? So the expression sine inverse x over 2 plus cos inverse x over 2 is equal to a pi over 2 due to this property. So now this expression can be written as a minus b times a plus b can now be replaced by pi over 2, and here we have lambda pi square over 4. So now we can write a minus b is equal to lambda pi square over 4 times 2 over pi. So this is now 2 times 2 is 4, and here pi and pi get cancelled. So we are left with lambda pi over 2. So now we have a minus b is equal to lambda pi over 2, right? Now from here we have a plus b is equal to pi over 2. So now let us write b is equal to pi by 2 minus a, and let us substitute this value of b in terms of a in this equation. So now we have a minus pi over 2 minus a, and here we have lambda pi over 2. So we have now a minus pi over 2 plus a, that is equal to lambda pi over 2. So a plus a is 2a, and here we have minus pi by 2, and this is a lambda pi over 2. Now taking this minus pi by 2 to this side, we have 2a is equal to lambda pi over 2 plus pi over 2. So now we can write a is equal to lambda pi over 4 plus pi over 4. Now let us substitute the value of a as sine inverse x over 2. So here we have sine inverse x over 2 for a, and this is equal to lambda pi over 4 plus pi over 4, right? So now we have arrived at this important result. So now let us apply the concept of the principal value branch of sine inverse theta. Now from inverse trigonometric functions, we know that sine inverse theta, it belongs to this interval, that is minus pi by 2 to pi by 2, where theta belongs to this interval, that is minus 1 to 1, right? So from here we can now frame the inequality, that is sine inverse theta is greater than or equal to minus pi by 2, but it is less than or equal to pi by 2. Now here we have theta is equal to x over 2. So now we can write minus pi over 2 less than or equal to sine inverse x over 2, and here we have pi over 2. So the range of sine inverse theta, it belongs to this closed interval minus pi by 2 to pi by 2. So now taking theta is equal to x over 2, sine inverse x over 2 has the range from minus pi by 2 to pi by 2, including both the endpoints. Now let us substitute the value of sine inverse x over 2 in this inequality. So we have minus pi over 2, and here we have lambda pi over 4 plus pi over 4, and here we have pi over 2, right? So now let us subtract pi over 4 throughout this inequality. So we have minus pi over 2 minus pi over 4, and here we have simply lambda pi over 4, because pi over 4 get cancelled because we are subtracting pi over 4 throughout, and here we have pi over 2 minus pi over 4. So now simplifying these two expressions, so here we have 4, then we have here minus 2 pi, and here we have minus pi, and here lambda pi over 4, and here we have 4 and 2 pi minus pi. So now we have minus 3 pi over 4 less than or equal to lambda pi over 4, and here we have pi over 4, right? So now let us multiply this inequality throughout by 4 over pi, so that here pi and pi get cancelled and 4 and 4 get cancelled. So now we have minus 3 pi by 4 multiplied with 4 over pi, and here we have lambda pi over 4 times 4 over pi, and here we have pi over 4 times 4 over pi. So here 4 and 4 get cancelled, pi and pi get cancelled, so we have simply minus 3, and here we have pi and pi get cancelled, 4 and 4 get cancelled, here we have simply lambda, and here we have a 1, because pi and pi get cancelled, 4 and 4 get cancelled. So we have now a lambda belonging to the interval that is from minus 3 to 1, right? So for all values of lambda belonging to this closed interval that is from minus 3 to 1, this expression is defined. So the required range for lambda is given by this interval, that is the closed interval from minus 3 to 1.